Hey, everybody. Today, we're going to develop some machinery to attack a particular problem. Let's say someone gives me an equation and I want to know if it has a solution, but it's important that the solutions be integers, not fractions, not decimals, but whole numbers. Can I solve that equation? It turns out that the answer to this question is given by a famous algorithm known as the Euclidean algorithm. So here's a question. Are there any integer solutions to the equation 4x plus 6y equals 1? We know that we can plot the line in the xy plane, so let's solve for y and get y equals 1/6 minus 2/3 x. Let's plot that line. And what we're really asking is, does this line hit any point on the integer lattice? But if we go back to the original equation 4x plus 6y equals 1, notice that if we plug in integers to the left-hand side, we always get an even number. So there's no way to get 1 on the right-hand side, because 1 is odd. So there is no solution. This line will not hit the lattice, no matter how far we extend it. Okay, what if we replace the 1 with a 2? And consider the equation 4x plus 6y equals 2. It turns out that this equation does have solutions. Today, we're going to show how to find all of the integer solutions to this equation. Let's start with the definition. Let m and n be integers that are not both 0. Then the greatest common divisor of m and n, sometimes written as GCD of m and n, is the largest positive number that divides both m and n. Where the name comes from, it divides both of them, so it's a common divisor, and it's defined to be the greatest one, so the greatest common divisor. If it turns out that the GCD of m and n is 1, we say that m and n are relatively prime. So here's an example. Let's let m equal 42 and n equals 63. We can write down all the divisors of 42 and 63. For 42, we have 1, 2, 3, 6, 7, 14, 21, and 42. We can check that all of these do divide, and if you mess around with it enough, you'll see that nothing else does. 63, we can get 1, 3, 7, 9, 21, 63. Same thing. The largest number that appears in both lists is 21, and that's the greatest common divisor. Okay? As a sanity check, let's check that 42 is 2 times 21, and 63 equals 3 times 21, so 21 is certainly a common divisor, and we can't make it bigger because 42 doesn't divide 63. Now we can see that we can find the greatest common divisor once we've written down every divisor of both numbers. But of course, in general, that's a lot of work, especially if the numbers are large. Is there a better way? It turns out that there is. This better way is known as the Euclidean algorithm. So we'll go through it in the abstract. Let's find the greatest common divisor of m and n. Let's assume that m is bigger than n. If not, we'll just flip the letters and compute the integer division of m over n using the division algorithm. Now, if R1 is 0 in this equation, n divides m and we're done. The answer is n, right? Because n divides itself and n divides m. But if it's not, what we do is now compute the integer division of n over R1, and we obtain a remainder R2. If this remainder is 0, we stop. If it's not, we keep going. We compute the integer division of R1 over R2 and get a remainder R3. We keep going on and on and on until we get a remainder of 0. Once we do that, we go back to the last non-zero remainder, and it turns out that that's the greatest common divisor. Now notice all of these q's, the quotients, they don't play a role in this calculation at this stage, although it'll be important to save those for later. Now as you look at all of this, what you should see is not necessarily why this gives us the greatest common divisor. It does, and there's a reason for it, but I would imagine that it's kind of opaque to most people right now. But just understand that this is an algorithm. I told you what to do in these steps. Eventually it'll terminate, and that'll give you an answer. It turns out we'll prove later that that gives you the correct answer. Let's work out an example. And here I want to pick some big numbers to make it a little bit harder. So let's look at the greatest common divisor of 3760 and 2961. So first you divide 2961 into 3760 and obtain a remainder of 799. We then divide 799 into 2961 and obtain a remainder of 564. Divide 564 into 799 and obtain a remainder of 235, and so on and so forth. 235 into 564 get a remainder of 94. 94 into 235 obtain a remainder of 47. Then finally, divide 47 into 94 and look, it divides evenly, so it has remainder 0. That means we go back to the last remainder we obtained, which is 47. That is the greatest common divisor. Okay, so now let's go back to the original question we posed at the top of the video. Can we solve the following equation? 3760x plus 2961y equals 47. And remember, we want to solve this for integers x and y. It turns out we can solve this equation, and we can obtain the solution by reusing the information we've already computed. So let's just look back at these equations over there, and notice that I've written 47 in terms of 94 and 235. And then the equation above that tells me I've written 94 in terms of 235 and 564. And I've written 235 in terms of 564 and 799. So basically I can back propagate all of this information and eventually, after some work, get 47 as a combination of 3760 and 2961. So it turns out this always works. Once we have the Euclidean algorithm, we can always back propagate in this way. And this gives us a corollary to the Euclidean algorithm, which is known as Bézout's identity. It says that as long as m and n are not both 0, then there exists a pair of integers x and y that solve the equation mx plus ny equals the greatest common divisor of m and n. And the proof is just back propagation from the Euclidean algorithm. So if we accept the Euclidean algorithm, which we will prove later, Bézout's identity gives us the answer. Okay, but let's make this a little bit harder. We found one integer solution to this equation, 3760x plus 2961y equals 47. Can we find them all? Okay, let's first simplify our life a little bit, and notice that we can divide this whole equation by 47. And when we divide this, we get 80x plus 63y equals 1. And we have a solution, the one we wrote down earlier. So let us try to find an integer solution to the same equation, not with a 1 on the right-hand side, but with a 0 on the right-hand side. So let's replace that equation with 80x plus 63y equals 0. Don't ask why right now, we'll get to that in a second. But once I have that equation is really easy, right? Remember this trick from Calc 3. When you want to find an orthogonal vector in R2, right, you just flip the coordinates and negate one. So for example, I pick x equals 63, y equals minus 80, and you can see when I plugged it in, they're going to cancel. And of course, it doesn't matter where I put the minus sign. I just did it this way. And this is just cooked up so that this works. So here's the idea, right? We have one solution that gives us 1. We have this other solution that gives us 0, but of course we can add a bunch of zeros to 1 and still get 1. So in fact, if we let x equals 26 plus 63t and y equals minus 33 minus 80t, where t is any integer, then we obtain a solution to this problem. We'll do one more example to tie it all together, but this time with nicer numbers. We want to find every integer solution of the equation 6x plus 15y equals 21. You see the numbers are a little bit nicer here. Let's first note that the GCD of 6 and 15 is 3. We can kind of do this one in our heads. 3 obviously divides 6 and 15, and 6 doesn't divide 15, so we can't go bigger than 3. So, by the Bézout identity, we can solve the equation 6x plus 15y equals 3. But notice, that's not quite the equation we started off with. But let's first of all figure out what that solution is. We'll write 15 equals 2 times 6 plus 3, using the division algorithm, and we see that we can solve for 3 and see that 3 is 115 minus 2 6s. So if we choose x equals minus 2 and y equals 1, this solves 6x plus 15y equals 3. But that's not the original equation. The original equation had a 21, but just multiply everything by 7. So what we do is we choose x equals minus 14 and y equals 7, And that solves 6x plus 15y equals 21. Now this gives one solution. What about the others? So we go back to the original equation, divide by the GCD, and then set the right-hand side equal to 0. And if we do that, you see that we get the equation 2x plus 5y equals 0. An obvious guess to take for that solution is the pair minus 5, 2. So our general solution is x equals minus 14 minus 5t, and y equals 7 plus 2t. That's a good place to stop, so I'll stop there.